So welcome, we're going to continue with our study of circular motion, and we're going to look at some specific examples, and there's basically 4 examples we tend to look at. In fact I'll just flip through and show you. We tend to look at soap on a rope on a level plane like a table or something like that, but with no friction. And then we look at what's called a conical pendulum underneath it, where it's kind of like not spinning as fast, but either way the tension is not radial to the middle of the circle, it's at some angle to that. And then we have a flat racetrack, that's the top right one, and the bottom right one is a banked racetrack. So 4 examples we like to talk about. Let's set this thing up. So we say Newton's second law should be applied to uniform circular motion, and I didn't bring my glasses, so this will be a bit cute. So Newton's second law is applied to uniform circular motion, and basically what we do is we say, consider a ball of mass m, so here's my mass m, tethered to a string of length r, so I have a radial distance, I have a mass. The ball travels with a speed of v meters per second, and the ball experiences a centripetal acceleration that points towards the center of the circle. We showed that before with our vector diagram. This acceleration is caused by the tension provided by the string. You need a force to cause an acceleration, and the tension is, in this point, doing one main job, which is providing the centripetal acceleration. If it was a vertical circle, then the tension would be doing 2 forces. It would be actually supporting the weight of the object, certainly on the bottom, and it will also be providing the centripetal acceleration. So we see it can get complicated, and so that's where we've got to go back to our analysis. We've got to look at our diagrams and analyze rather than trying to figure all that stuff out. We're going to remember the AC, my centripetal acceleration. This is what I owe. This is my bill. This is my check, my debt, is v squared over r. And we remember that Newton's second law, F equals ma. Certainly there's an acceleration taking place in the plane of the motion. And here's a tip. Although the diagrams that I give you won't necessarily have this orientation, I find it really helpful if you always picture this motion from the side, so you're looking in that direction. There's your eyeball looking up. And it's really good to picture it with the mass on the left-hand side, so that the acceleration is positive direction, the tension is a positive direction. Because otherwise you've got negative signs in there that should be there, and if you mess up on the negative signs, if you remember it in one case, if I put the thing on this side, then it's a negative acceleration. AC is negative, and my tension T has a negative sign in front of it. And you might remember in one and forget in the other, and then you're done for. So it's a really good idea to put your mass on the left-hand side of your diagram, so that when you look at this instant and you do your analysis, you've got positive parameters. We're going to apply basically that. That's all we're going to do. Apply that for 4 different times. And so let's go through them. So a 2-kilogram ball is attached to the end of a 4-meter long string. The ball moves in a horizontal plane. The string can withstand a tension of 80 newtons. What is the maximum speed that the ball can attain before the string breaks? So it's a little bit interesting. There's our string, we have a tension. Of course we have an AC, and we have a mass, and then we have a radius. And I want to kind of show the velocity, or the speed if you like. I'm going to kind of show it kind of like that. Okay? And that's my speed v. It's coming towards me. I'm looking for the side and it's coming towards me, kind of thing. And what do I know? I know m is equal to 2 kilograms. I know that r is equal to 4 meters. I know that T is equal to 80 newtons. Now, T can be changing depending upon how fast I'm going. So T could be anything, but I'm taking the special case where this is about to break. And so I know when this is about to break, it says, what is the maximum speed Well, the maximum speed is when it's about to break. That can be attained before the spring breaks. So I'm taking that special case where my speed is maximum, which means my T is maximum, which means my T is 80 newtons, because it says the string can withstand a tension of 80 newtons. So there's a little bit of, conceptualization there. It's not just like plugging into an equation. And then I want to know my V. What is my V? So let's try and link these guys together. And I know that, Newton's second law. The sum of the forces horizontally is equal to ma. That's true. But I'm going in a circle. So that equals mac. Let's be specific, because I'm going in a circle. This is a centripetal acceleration. And this equals mv squared over r. Okay? So I went from Newton's second law. I recognize that I'm in a circular motion situation, so I need to have the centripetal acceleration, not just I recognize that the acceleration was centripetal. And then I can put in the terminology for the centripetal acceleration, which is v squared over r. So then I look at my diagram, and I say I'm resolving forces horizontally, and the only horizontal force I have is plus t. It turns out in this case there's no minus force, there's just this. If I want a smooth table, then there could be a normal force upwards, but that's perpendicular to this thing. I tend to think of it as you spin it, and you manage not to get a cone, but you manage to get a flat plate. That's the pure way of looking at it, but that's hard to do actually physically. So sometimes people will say you're on a smooth table. So there's no friction, it's just the weight and the upwards force. And they will just cancel each other out. Either way, they're at 90 degrees to our plane of interest, which is the horizontal axis. So it's plus t, and this equals my mass, which is mv squared over r. And I want to find my v squared. So do I put numbers in first or do I range first? This looks pretty straightforward. So I'm going to say v squared is equal to tr over m. So v, I'm going to go over here, v is equal to the square root of tr over m, which equals the square root of t, and that's 80, times r, and r is 4, over m, and m is 2. So that's going to be the square root of 160, which equals, and it's not 400, is it? So, not 40, is it? Second square root, 160 is equal to 12.65 meters per second. So there's my answer. So it's there, E. So look at the approach. I started off by visualizing, as I always do. I did a diagram, and if you don't do a diagram, you will sometimes get confused. I did a diagram. I basically was a bit mindful. I practiced this beforehand, so I know there's an advantage in always putting the mass at the right and at the left-hand side, and have the centripetal acceleration go to the right because of science. But there's no law that says you have to do it that way. I made a list. By making a list, it always reminds me of what my parameters are, and that jogs my memory as far as my equation is concerned. And then I recognize, well, this is a Newton's second law situation, so it's the sum of the forces equals ma in the horizontal direction. And then I recognize it's a centripetal acceleration, so it's mac. And then I remembered that ac equals v squared over r, so I substituted that in. So it's a two-step problem in a way, yeah? Two equations. Rearranged, put my numbers in. Putting the numbers in is like, you've got to be able to do it, but it's not really the physicsy bit. The physicsy bit is setting it off. So, but that approach. Let's jump out of here. Actually, can you do that one for me, please? Let's get you guys involved. So we're back. Let's stop this and have a quick look. I got to do something. Let's stop this and have a quick look. Oh, didn't mean to do that. Oh, I think I've lost everything. Yeah. As you were. I don't know what people said. Yeah. I actually went to bed early last night. I went to bed at about 11 o'clock, so I don't know. Sorry about that. I'll wonder forever what the answer would have been. But so a ball is attached. So let's have a look. So a ball is attached to the end of a string. 7 meters long, and you can see after a while, I'm kind of like doing the same. Tension is 35. T equals 35 newtons. We're in the same diagram all the time. This is mass. That's what I want to find. And this velocity down here is 9 meters per second. It's a tangential velocity, or we could call it speed. So m is, I don't know, and t is 35 newtons, and speed is 9 meters per second, and r equals 7 meters. So then I say, well, the sum of the forces horizontally is equals ma, and this is a circular motion problem, so it's mac, which equals mv squared over r. And when I look at this, I've only got the t is equal to mv squared over r. So in this case, we have plus 35 is equal to my mass times my velocity squared, speed squared if you like. So that's going to be 9 squared over 7. So m is equal to 35 times 7 over 49. So that's going to be equal to 35 times 7, enter, divided by 49, enter. And I'm getting 5. That can't be right. So let me check it again. 35 times 7, enter, divided by 49, enter. That's better. Oh no? So what am I doing wrong? Oh, 81. Okay. I'll put down 7. Yeah. So 35 times 7 over 81. Oh well. I'm going to just erase this when I go home. It's like times 7 divided by 81. Kilograms. Cool. So not bad. There's only so many things I can do with a question. I can change the words to describe it, but I've got to give you all the information. I've got to give you everything apart from one thing. Maybe I can give you a little bit extra. I can confuse you by telling you the temperature or something, but and then I've got to ask you for one thing, and there's always going to be a relationship between them, and it's just the rest is just rearranging and sorting it out. So don't ever let yourself be put into a corner where you say, I can't possibly do that. You can. There's certain rules. It's not magic. There's certain rules that I have to follow. A car is moving on a flat horizontal track, makes a turn of 2 meters, a 0.8 coefficient of static friction exists between the tires and the track. What is the maximum speed that the car can have while while driving around the track? So, okay, there's our car. I have my mass of the car. I have my radius. I have some kind of force. In this case, it will be FF. Remember, this thing wants to go in a straight line, and you're making it go in the thing, and the tendency is to go there, and you're making it go there. So it's the frictional force is towards the center of the circle. Okay, and I have a certain speed on this, and my speed on this is v. And I say, well, let's have a look. The sum of the forces horizontally equals ma. which equals MAC, which equals M times V squared over R. Okay, I know that. Where's my list? So I was stood there and I was thinking, I have no idea what I'm trying to find in this question. So let's make my list and I'll know. So 6 kilogram flat horizontal track, radius equals 2 meters. Coefficient of friction, okay, I got to do something with that, maybe, maybe not. No units, of course, on that. What is the maximum speed? V is what I want. Maximum speed means I'm on the point of slipping. That the car can have while driving around the track. Okay, so there's my list. So let's have a look. I don't know my V. I need to know my FF. So then let's go into. So here's my weight, and if that's a 6 kilogram car, that's a 60 Newton weight, and that means I have a 60 Newton normal force, and my force of friction is in that direction, and I say FF is less than or equal to mu s times Fn. Whoa, hold on. Isn't that the equation for static friction? Yes. Isn't this thing moving? Yes. So why am I using the equation for static friction? And it's a little bit subtle, but the friction is not about the vehicle. The friction is about the tire. And when you roll your tires, what happens is this piece of tire is placed on the road and then lifted off. Unless you squeal your tires, you're not sliding. If your tires are squealing, then you're in kinetic friction, because the tire is moving relative, scraping across the road. That's kinetic friction. When the block slides along the table, that's kinetic friction. When the tire slides along the road, that's kinetic friction. But when you're driving normally, you place the tire and lift the tire up and place the tire. So as far as the road's concerned, this thing comes down and then meshes and lifts off. It never slides. So it's static friction. So it's a little bit, seems a bit counterintuitive, but it is static friction. And that's why it has to say on the point of slipping. Because I know on the point of slipping that FF is equal to mu s times Fn on point of slipping, opos. So I can say, okay, my FF is equal to 0.8 times 60. Am I okay with that? It's nice and level, so my weight is going to equal my normal force because I'm on a level track. So that's going to be times 60. 6 eighths are 48, so that would be 48 newtons. So then I say, in that case then, FF is equal to 48 newtons. So then I say, okay, let's have a look at this then. So I'm going to say FF is equal to mv squared over r. So I'm going to say 48 is equal to 6 v squared over, where is it, 2. So v squared is equal to 48 times 2 over 6, which equals 116. Is that right? 3 sixes are 18, yeah? 16. So v is equal to the square root of 16, which equals plus or minus 4 meters per second. In this case, speeds are not vectors, so it's going to be it's a scalar. It's going to be a magnitude, yeah. So it's going to be just 4 meters per second. So if you think about it, when you get to the stage where you can do these, you need to pat yourself on the back because you're doing a multi-step problem. It's not just F equals ma. It's two equations, F equals ma, and it's AC equals V squared over R. It's actually three equations because we have the sum of the frictional force is less than or equal to mu s times Fn. So there's three different bits of physics coming into play, and you're putting them together. And if you try and remember that, then, you know, I think good luck, because there's so many bits to remember. What I remember is the approach. I do my visualization, I recognized, oh, this is Newton's second law horizontally. Oh, it's a circular effect, that's V squared over R. Oh, I need to find the force of friction. I know. I'm just tapping little bits of work that I have. And that's why, to be preachy a little bit, that's why, you know, maintaining pressure on yourself to keep learning throughout the course is really important. Because if you squared away your force of friction stuff, if you kind of mastered that, it's in your back pocket, it's easy. If that's wobbly, and you're adding it to this, it just like becomes, it's like balancing books on top of each other, and none of them are really nice and steady. It just gets harder and harder and harder. So it's really worthwhile, not the night before the test, but the night after the test, to really get stuck in and kind of like keep on mastering. It will get easier. You know, it's one of those things. It just gets, if you do it, it gets easier and easier and easier. If you put it off, it gets harder and harder and harder. I don't want to get on today, so I'm going to assume that we're okay on that. I want to get onto one of these. I just want to give you a bit more practice on one of the harder ones. These next two are a little bit harder because they involve some trig. And if you've mastered the trig, it's no problem. Throw it at me. I can do cosines and sines. If you've not mastered components, it's like, this is a disaster because, you know, this is the thing I can't do. So you got to master these things as you see them. Don't leave the stuff unresolved because it's going to come back. So a 6 kilogram ball is attached to the end of a long string. The ball revolves. There's rotation. I think of as rotation as on an axis. I think of as revolvement as going around an axis. So the ball revolves. That's just me, I think, more than anything else. I like to separate the two. With a constant speed of 3 meters per second in a 4-meter radius horizontal circle that forms a conical pendulum. Find the angle. Oh, this is hard in a number of ways. Find the angle that the string makes to the horizontal. So first of all, let's do ourselves a diagram. So I'm going to draw the physical setup. So there's my conical pendulum. I'm picturing it when it's at the left-hand extreme. And of course I have a tension. Let's actually, I'm gonna be a bit, so that's 4 meters here. That's 4 meters. And let's have a look. Find the angle that the string makes to the horizontal. So there's the angle I'm trying to find. And I know I have this tension. And I know I have the mass. And my diagram's going to be a bit complicated, so I'm not going to put in the velocity because I need the vertical really to be clean. So I'm kind of going to do it like that. I'm going to say my V, there's my V. What do I know? I know that M is equal to 6 kilograms. I know that V, my speed, is equal to 3 meters per second. I know that my radius, R, is equal to 4 meters. And I want to know the angle, theta. Okay. So the problem is it's asking for angles, so it's kind of like, it don't really tell you where to begin. But I've practiced these things, so I'm going to begin by looking at centripetal acceleration. So I'm going to say the sum of the forces horizontally is equal to ma, which equals, well, it's centripetal acceleration, so it's mac, which equals mv squared over r. Same old, same old. But now, this is not t. What is my, let's do this in a different colour because it's a bit of thinking that I need to be clear about. It's not going to be t, it's going to be t cosine theta. And what I need to do is I need to recognise that if that's the length of my t arrow, I need the component of that t arrow along the horizontal axis. The sum of the forces horizontal. And that's why, can you see how, and this is just, you know, what you learn the hard way is by specifying the direction. When you say the sum of the forces, by specifying the direction, it brings to mind what direction you should be working in. It kind of tells you what direction you should be working in. So then if you use something in another direction, an alarm bell goes off in your head. So if you say to yourself, the sum of the forces equals ma, but you never say which direction, you're more likely to put things in that are not on the same axis, in which case it's completely wrong. But if you say the sum of the forces horizontal, or the sum of the forces vertical, or the sum of the forces down the slope, or the sum of the forces perpendicular to the slope, if you kind of go that extra step of being a bit picky, it just puts an alarm bell so that when you're not working horizontally, but you said you were, then you know, hey, there's something wrong here. You know? And so, and again, two colours helps really nice. Can you see how my tension in black kind of distinguishes itself from the radius? Because it's amazing, people will sometimes look at the triangle and say, oh yeah, but that sideways force is 4. But you go, that's 4 meters, and go, yeah, but that's how big the triangle is. And it's like getting force diagrams and position diagrams all mixed in together. And it's understandable when you first begin. But this is a diagram that contains the position stuff in red and the force stuff in black. And so, in fact, I'm going to do some more stuff in a minute that's even slightly different. So this is t cosine theta is equal to, and this is going to equal, let's have a look, my mass, which is, well, let's leave it, m v squared over r. Let's see if I can get some stuff to cancel out a little bit. Okay. Let me put numbers in, and then I know that I'm stuck. So m is 6, and v squared is 3 squared, which is 9, and r is 4. And I got a problem. And the problem is, I don't know t, and I don't know theta. Mathematically, I need to find t. So I'm going to change colour pen. Let's go to blue. And okay, well, this thing has a weight, so that's going to be 60 newtons equals Fg. And there's going to be, but I'm going to go back to black now. Oh, so this is going to be t sine theta, whereas this down here was t cosine theta. Okay. So I can say, okay, for this bit, I'm going to say the sum of the forces vertically equals 0. It's not accelerating up or accelerating down, it's going in a circle, horizontal circle. So I look at my diagram and I go, oh, plus t sine theta added to minus 60 is equal to 0. So the simple way is I go t is equal to 60 divided by sine theta. Let's substitute in. So I'm going to say 60 over sine theta times the cosine of theta is equal to 6 nines, 3 threes are 9, 1.5 times 9 is 13.5. Yeah? Yep. That goes from there to there. So cosine theta over sine theta is equal to 13.5 over 60. Which equals 13.5 over 60. So what is that? That's going to be 13.5 divided by 60, which equals 0.225. Let me just double check I've done this the right way around. Yes, it looks like that. Yes, yes, yes. So then I say, okay, I want to find theta. Cosine, adjacent over hypotenuse. Sine, opposite over hypotenuse. So I'm going to say cosine theta over sine theta is like adjacent over hypotenuse over opposite over hypotenuse, which equals adjacent over opposite. Agreed? And tangent theta is equal to opposite over adjacent. Yep. So I can say, oh, tan theta is equal to 60 over 13.5, which equals the inverse of what I just took. So where's my inverse on? He is there. So that would equal 4.44. And so theta is equal to tan to the minus 1 of 4.44, which equals second tangent, second answer. And that's going to be 77.3 degrees. Am I right? Well, at least the answer's there. I mean, it's like, I never remember what the right answer is, but at least the answer's there. Writing all over the place. Yes?
Cosine over sine, isn't that cotangent?
Yeah, I guess. I never bothered with that. Cotangent is 1 over the tangent. That's what it says. Yeah, flipped it. Yeah. So keep it simple. Unless you want to be a mathematician. No, I shouldn't say that. I didn't say that. Am I still recording? Yeah. So, but you know, make it a bit more straightforward. So there's that bit. Now it's beginning to look a bit more manageable. I have a first calculation, a second calculation, and I'm messing with a third calculation. And most of the writing is all to do with this angle stuff. You know, it's like those are a bit harder because when it says what's the angle, it's like where do you begin? There's not an obvious thing about. There's 1,000 equations that have theta in it, so you've got to have some way of beginning, and it's like one of those leaps of faith. One of my friends who's a faculty member at USF on many teaches upper division courses says there's a progression, and he says that people start off and they're like math and they're good at it, so they continue, and people like science, so they're good at it and they continue, and then in physics 1 they're kind of putting the math and the science visualization together, and they've got to build their skills on that. But by and large, they can recognize the problems and recognize the solution. And if they're smart, they don't recognize the actual problem specifically. They recognize the type of problem and they know the approach. It's not that, if I took the smartest class and never showed them any of this, but just told them, Newton's laws and, if I taught them the physics without showing them practice examples, and then said, okay, you've done it, let's give you a test, people would do quite poorly. Because you learn a lot by doing the practice, and you learn these insights that you wouldn't normally just think of by yourself. So my job, as part of my job, I used to teach people AP Physics, which was an exam not set by me. And part of my job was to recognize what kind of things come up and practice those things. That's part of it. It's like it's teaching to the test, but if the test is a good test, that's a good thing to do. You write a test that's really meaningful, and then teach to it, and you'll do great. So part of it is our training of going through these things, and that's fine. But if you get the approach, it goes well. But then, so with this, it's not obvious, but with practice, it's the approach. And then he says, in the upper division courses, you tend to get to the stage where you're given problems, and there's no way you can kind of see your way through it from the very beginning. You have to say, well, I know how to make this step, and then you look and now I know how to make that step. Oh, now I know how to make that step. So it's letting go of, I know the answer, I'm just going to fill the work in, to I'm going to start on this journey, which is the problem, and I'm going to find my way to the end. And he says it takes guts to kind of head off in that direction when you don't really know what the answer is going to be. And that's training. It's kind of like, okay, I know to do this bit, and then I'll reevaluate. And we're beginning that here, aren't we? We're doing bits and bits and bits. And I think the smart money is, it's about circular motion, and you've kind of seen it before. You don't remember exactly, but I'm going to be involved. So the problem I have is, if you look at my videos, I might have solved this in a different order. There's a thing you can do where you say, sine theta over cosine theta equals tan theta. So then you just take those two bits and you don't even bother with this bit down here. You just take those two equations, divide that equation by that equation, and get you the answer more quickly. But it's a bit like pulling a rabbit out of the hat if you don't spot that relationship. So it's more challenging, but that's what we're training for. And I want to do the last one. What I'm going to do is the last one, and I'm going to let you have a go at it as well. So this last one is somewhat similar. It's basically a different diagram. It says a 4-kilogram car moves on a banked circular track that has a radius of 5 meters. The banking is designed so that the car does not rely upon static friction. Have you ever been on 275 and sometimes you'll go around a corner and you didn't really change the steering wheel? You just drove in your lane. And they bank those tracks, they bank those lanes so that if you're doing about the speed limit, you will not need to adjust. You just continue around. And in fact, one time, let me do this. Okay, so what we have is a 4-kilogram car. So let's draw it again, and here again, try and make your car over onto the one side, and a big diagram. So remember what the situation is: a little box with big arrows. So there's my car, and it moves on a banked circular track. That's a radius of 5 meters. Now, from the car, that's a little bit of stuff you've got to be able to. In fact, you can't do it any other way. So from the car to the middle of the track must be 5 meters, not from the edge of the track, because then you don't know how far the car is away. So the radius is talking about is that. The banking is designed so that the car does not rely upon static friction. Okay, so there's no FF. At optimum speed, if the track is banked at 20 degrees to the horizontal, so this is 20. What is the optimum speed? So let's have a look. I know my M is equal to 4 kilograms. I know my theta is equal to 20 degrees. I know my R is equal to 5 meters. Let's finish off our diagram. We've kind of been a bit lax on our diagram. It's not a complete diagram. I certainly have a weight in here, and that weight, Fg, is going to equal 4 kilogram car. That's 40 newtons. Now, this is a case where we also have a normal force. When you sit one thing on top of another, you have a normal force. The normal force must be perpendicular to the surface, and that is not equal to 40 newtons. This is one of those cases where you can't just say, oh yeah, the weight's 40, the normal force is 40, because they're not on a flat surface. Okay, so let's see if we can make a start on this. We can say the sum of the forces horizontally equals MA, which equals MAC, which equals MV squared over R. Let's come down here and let's recognize I need my horizontal component of that force, which would be Fn. Now here's a bit of a geometry bit. If that's 20, that's 20, and if that's 20, that's 20, and if that's 20, this is going to be a sine theta. So let's look. If that's 20 down here, that's 20 up there. If that's 20, that's 90 minus 20. If that's 90 minus 20, that's 20. And notice how, because I deliberately didn't draw my things at 45 degrees, I have a big angle and a little angle. So I go, oh, the little angle there is 20, that means the little angle there is 20, which means the little angle there is 20. So it's a real advantage in not doing everything at 45 degrees. It's a real pain. I'll give you a diagram at 45 degrees because I want to see if you can do it. But, you know, my diagram is going to be really poor. I'm giving you a diagram which is deliberately just to give you the conceptual idea. I'm not trying to give you a good diagram to work with. So a bit of components in there. So I say, okay, well then that means that Fn sine theta is equal to mv squared over r. Let's have a look. What do we know? We don't know what Fn is. We don't know what. Oh, we do know what sine theta is. So Fn sine 20 is equal to my m, which is 4. I want to find my v squared, isn't it? What is the speed? Yeah, I want to find my v. So v squared over, and my radius is 5. Okay. Oh, two unknowns. Let's rearrange it. So v squared is equal to 5 over 4 Fn sine 20, and I can work out the sine 20 if I want. It's just a decimal number. I'm going to leave it like that for the minute. I'm going to change coloured pens. Let's go to a blue pen. I'm going to say, sorry, a blue pen. I'm going to say, okay, well, find Fn using the sum of the forces vertically equals 0. So I'm going to say this is going to be Fn cosine theta. So I'm going to say plus Fn cosine theta added to minus 40, because that's my weight, is equal to 0. So Fn cosine theta is equal to 40. So Fn is equal to 40 over cosine of 20. And I just feel like working that out. So that's 40 divided by cosine 20 equals and I'm getting 42.57. So now I substitute in. So I'll come along. So I'm going to say v squared is equal to 5 over 4, 42.57. What is sine 20? So that's going to be 0.34. So v squared is equal to, let's work all that out, 5 times 42.57 times 0.34 equals, divided by 4 equals 18.09. So v is equal to the square root of 18.09. So v is equal to second square root, second answer, 4.25 I've got. Hopefully that answers there. 4.5, sorry, 4.25, 4.27 I've got, which I think is close enough. That would be meters per second, unless I made a mistake, but I don't think I did. So you see that we have a nice setup. It's like we have our list, we did a decent diagram, we tried to solve it, we realized we needed to find out what our normal force was, and then we solved it. So by just breaking it up into these thoughts, it comes out, okay? Okay. Cool. I want to let you have a go at something similar. So can you do that one for me, please? A 2 kilogram car moves on a bank track that has a radius of 3 meters. The banking is designed so that the car does not rely upon static friction when the speed is that. What is the angle of the track? Oh, I'm going to talk you through this, okay? So we're back, and while we were off the recording, we went through this. So let's just recap. So we do a decent diagram, and then I'm trying to find an angle. So I know I'm going to have to compare horizontal and vertical. The only way I know how to do these is I'm going to do the horizontal thing, because that's where the acceleration is. I'm not going to be able to solve it, so I'm going to do the vertical thing because it's the only thing left. So this pattern is the sum of the forces horizontal equals, well in this case, MA, which equals MB squared over R. I take that as far as I can, and I don't freak out because I can't solve it. It's just I don't know Fn and I don't know the angle. I need two unknowns, require another equation. Let's go vertically. We go vertically, sum of the forces vertically equals 0. Again, work through it from a decent diagram and you get a numerical value. And then I just recognize, like I mentioned before, oh yeah, sine theta over cosine theta is tangent of theta, because opposite over hypotenuse divided by adjacent over hypotenuse is opposite over adjacent, which is a tangent. So that means that I can put one equation divided by the other. Remember to cross out my FNs. Look, I nearly didn't. I was so concerned about the angle, I nearly put down that it was Fn tangent theta. Because I'd written this down, my eye told me, no. It had a little alarm bell, so then I could cross those guys out. And then I'm just doing a tangent, inverse tangent, and I get my answer. So it looks horrendous, but by just going it step by step, a decent diagram. Without a decent diagram, I cannot do these. I cannot do them. It is step one. I cannot do them. And you know, if you can, power to you. You're kind of like, you're more analytical than I am because I cannot do them. If you cannot do them, then why not, steal from me? Rather than going through the 18 months I went through, just learn now. A diagram's going to help. Do a decent diagram, practice your diagrams, and if you get stuck on the diagram, that's important. Come to my office and we'll go through diagrams because it's a skill. You do far more complicated things every day. It's just that you do them, you do practice them. So if your diagram's not up to scratch, then work on it, because it will improve things. But you do a decent diagram, and then the two principles are, I need an equation to solve this. Let's go with the acceleration. Oh, it didn't work. I didn't get the total answer. Then I need something that's independent. I need a second equation that's independent. And the only axis which is independent of the acceleration is at 90 degrees to it. And I know the sum of the forces equals 0. And we've used that now for a couple of lessons. We've gone with the acceleration and then went 90 degrees to it. We just happen to be doing it in a circular motion context. This is really Newton's second law. It's just the same equations. It's a dynamics problem. It's a Newton's second law problem. The only wrinkle is you know the acceleration is v squared over r. In approach, it's very similar to what we've been doing so far. Cool. So is that the end of it? Let's have a look. Oh, a little bit more. Non-uniform circular motion. And, you know, this is not even more complicated. It might sound like it is, but again, non-uniform circular motion is made up of two components. Non-uniform circular motion means that your speed is increasing. And if your speed in a direction increases instantaneously, which it must be happening every instant, you're going a little bit faster at the end of the instant than you were at the beginning of the instant, so your speed is increasing during that instant, that means you have an acceleration. And it's a tangential acceleration. If I'm going round and round in a circle, my velocity is in this direction, and my acceleration is in that direction. I'm speeding up going around the circle. If I'm going round in a circle and my acceleration is behind me, I'm slowing down going round in a circle. Either way, it can be represented as a tangential acceleration. Because I'm going in a circle, I do have a centripetal acceleration. If ever you are going in a circle, there must be a centripetal acceleration. And so my overall acceleration is now a sum of these two. Uniform circular motion, the purple bit is not there. It's just the centripetal acceleration. If I cut the string, then the blue bit's not there. I'm going straight forward. Combine the two of them, I have my overall acceleration, which is the purple bit. And it's just Pythagoras. So it's going to be, the total acceleration is equal to the square root of a tangential squared plus a centripetal squared. It's just like that, basically. So it looks like it's going to be hard, but actually there's not that much I can do with it. At time t equals 0, a 3 kilogram particle travels at 8 meters per second around a circular path of radius 4 meters. So I need to visualize here. A lot of writing, so let's have a look. There's my particle. It's 3 kilograms, and it's going round, and it has a speed of 8 meters per second. Radius is 4 meters. Particle has a tangential acceleration. Let's change colored pens so that I don't get these two guys confused. So I've got a black, and that's going to be my A is equal to 5 meters per second squared. Okay. What is the particle's net acceleration, and what is the angle between the particles? So let's visualize it. So traveling in that direction, and my acceleration is in that direction. So I'm going to have a tangential. That's going to be 5 meters per second squared. And I'm going to have a centripetal, and this is going to be v squared over r. This is my A. And it says, what is the angle between the particle's net acceleration? That's what I've just found out. That's my A. And the particle's centripetal acceleration, so I want that. So I can say, okay, A centripetal is equal to v squared over r, which equals, I didn't do my list, but maybe my diagram's going to be good enough for me. 8 squared over 4. Which is 8 8s are 64, divided by 4 is probably 16, I think. So that's going to be 16. meters per second squared. So A is equal to the square root of a t squared plus a c squared. Doesn't really matter, does it, which order it's in, which equals a t squared is 5 squared plus 16 squared. I do like to keep them in the same order once I've done them, which equals square root of 25 plus 16 squared, 256, which equals square root of 276, 281. Second square root of 281 equals 16.76. So there's one answer. Hopefully that's down there somewhere. And then tan theta is equal to opposite over adjacent, which equals 5 over, not 16.76. That's a common mistake. People kind of like they've got it in their mind. But the fact of the matter is they worked out that it was 16. So that gives that theta equals tan to the minus 1 of 5 over 16, which equals second tangent 5 divided by 16, close your bracket, and that's going to be 17.35. And if you're in degrees, it's going to be in degrees, and if you're in radians, it's going to be in radians. As long as you put down the right unit, it's the correct answer. So what is this? This is going to be about 16.8 and 17. It's A, isn't it? So not bad. It's just really an exercise in visualization. Do you know what the words mean for? And then just a little bit of Pythagoras and trigonometry. This is the next one. Oh, I better check on my time. Oh, stop.